Okay, let me continue with Caley-Hamilton theorem. Actually, I was running out of space in my mobile. I could not make this video complete. Let me complete it now. So, Caley-Hamilton theorem. It states that every square matrix satisfies its characteristic equation. I have already given the definition in my previous talk. Let me give an example. Let A equal, say, 1, 2, 3, 4. You see, every square matrix satisfies its characteristic equation. So we have to find the characteristic equation. The characteristic matrix of A is given by A minus lambda I, which is nothing but 1 minus lambda, 2, 3, 4 minus lambda. Okay, and the characteristic equation is determinant of A minus lambda I equal to 0, which means determinant of 1 minus lambda, 2, 3, 4 minus lambda equal to 0. Fine. Or 1 minus lambda into 4 minus lambda minus 6 is equal to 0. Or this is minus minus plus lambda square minus 5 lambda plus 4 minus 6, which is minus 2 equal to 0. Minus minus plus lambda square minus 4 lambda minus lambda is minus 5 lambda. Then 4 ones are 4 minus 6, it is 2. This is the characteristic equation. Now what is by Caley-Hamilton theorem? Every square matrix satisfies its characteristic equation. So by Caley-Hamilton theorem, we should have A square minus 5A minus 2I is equal to 0. This is the definition of Caley-Hamilton theorem. Every square matrix A, this is A square matrix of order 2, satisfies its characteristic equation. It satisfies. In the stead of lambda, if we put lambda equal to A, this will be 0. Let me verify it. This is always true, but for you, let me verify it. You see, in order to verify it, I have to find A square. To verify it, verify Caley-Hamilton theorem, I have to show that A square minus 5A minus 2I is 0. This is always true. We can always write it by Caley-Hamilton theorem. This will be 0 because its characteristic equation is lambda square minus 5 lambda minus 2. So every square matrix satisfies its characteristic equation. Therefore, A square minus 5A minus 2I will be 0. But in order to verify it, to show you that this is always true, let me find A square. Now A square is equal to 1, 2, 3, 4. 1, 2, 3, 4. Now let me multiply it out. This is equal to 1 into 1, 3, 2, 6. So it is 7. 1 to 3, 3, 4, 12. So it is 15. 2, 1, 2, 4, 2, 8. It's 11. Sorry, 10. 2, 1, 2, 4, 2, 8. 2 plus 8 is 10. Then 2, 3, 6. 4, 4, 16. 16 plus 6 is 22. This is A square. Now let me take left hand side. Left hand side is A square minus 5A minus 2I, which is equal to 7, 10, 15, 22 minus 5 times A. Your A is 1, 2, 3, 4 and minus 2I, 2, 1, 0, 0, 1. So this is equal to 7, 10, 15, 22 minus 5, 1, 5, 5, 2, 10, 5, 3, 15, 5, 4, 20 minus 2002. So finally this is 7, 10, 15, 22 minus this is minus 5 and minus 2, it is minus 7. 10 plus 0, it is 10. 15 plus 0, it is 15. 22 plus 2, 22. So this is 0, 0, 0, 0. So this is true that every square matrix satisfies its characteristic equation. Now, what now? If this is true, using Caley-Hamilton theorem, we can find inverse of a matrix. Now how? Let me tell you. So let me find inverse of A 1, 2, 3, 4 using Caley-Hamilton theorem. See, if I have to proceed to find an inverse of a matrix by Caley-Hamilton theorem, first of all I have to find the characteristic equation of A. See, the characteristic equation of A is what? Lambda square 5 lambda minus 2 equals 0. By Caley-Hamilton theorem, which we have already seen and which we have already verified, I have every square matrix satisfies this characteristic equation. I have A square minus 5a minus 2i equals 0. And I have told you already this 0 and this 0 are different. Now this gives us 2i is equal to A square minus 5a. What we are going to find is that we have to find the inverse. So this is 2i equal to A into A minus 5i, because you know A into I is A, so I can always write it as A common liya हमने, so A minus 5i. Let me pre-multiply both sides by A inverse. Pre-multiply by A inverse. What I will get? 2i into A inverse is A inverse into A minus 5i, which gives us A inverse is equal, or twice A inverse is equal, A minus 5i. Now let me find A minus 5i so that I can find inverse. So twice A inverse, this gives us A is 1, 2, 3, 4. 5 times I, 1, 0, 0, 1. Or let me write 5 times I is 5. Okay, so this is equal to 1 minus 5 is minus 4, 2 minus 0 is 0, 3 minus 0 is 3, 4 minus 5 minus 1 by 2. So your A inverse is 1 by 2. You see, A inverse is adjoint A by determinant of A. You can see determinant of A is minus 2. You can take it outside. This you can write it as minus times over 2 minus 2 minus 3 plus 1 by minus 2, because your determinant A is 4 minus 6, which is minus 2. So this is adjoint A by determinant of A. You can have, this is also your inverse, this is also the inverse. Fine? So using Caley-Hamilton theorem, you can always find inverse of a matrix. Let me take up one more question. Find the inverse of, using Caley-Hamilton theorem, find inverse of A equal, say you have 2 minus 1, 1, minus 1, 1, symmetric matrix. This is this we have already done in our previous lecture. This question we have already found the characteristic equation of A. So I will write down the characteristic equation of A. The characteristic equation of A is given by determinant of A minus lambda I equals 0, which means 2 minus lambda minus 1 1 minus 1 2 minus lambda 1 minus 1 2 minus lambda is equal to 0, which means lambda cube minus 6 lambda square plus 9 lambda minus 4 equals 0. This we have already done in our previous lecture, so I don't have to expand it and obtain this. So I know the characteristic equation of this matrix is given by this. Now by Caley-Hamilton theorem, you can always verify it. I will now write by Caley-Hamilton theorem, a cube minus 6a square plus 9a minus 4i is equal to 0. I have to find the inverse, or 4i is equal to a cube minus 6a square plus 9a. Or 4i into a inverse is equal to a inverse into a square minus 6a plus 9i, because you can always write a as a into I. Okay, so 4a inverse is equal to a square minus 6a plus 9i. Now let me find out what is a square. This is 1, say. Now a square is equal, because I don't know a square. I know a, I know I don't know a square. So a square will be 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2 2 minus 1 1 minus 1 2 minus 1 1 minus 1 and 2. So let me find out the product. This is equal to 2 to 4 plus 1 plus 1, it is 6. 2 1 2 minus 2 and minus 1 is minus 5. 2 plus 1 and 2 is 5. Now this one, minus 2 and minus 1, so it is minus 5. Minus minus plus 2 plus 4 plus 1 is 6. Minus minus plus 2 to 4 1, so 6. Minus 1 minus 2 and minus 2 is minus 5. Minus 1 minus 2 and minus 2. Then last one is 2 plus 1 plus 2 is 2 plus 1 plus 2 is 5. Then minus 1 minus 2 and minus 2 is minus 5. Then 1 plus 1 plus 4 is 6. This is a square. Now let me verify, let me find the a inverse. A inverse from 1. Now from 1. For a inverse is a square. This is a square. 6 minus 5 5 minus 5 5. This is symmetric matrix, that is why it has come out like this. 6 minus 5 minus 5 and 6 minus 6 a is 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. Then 9i 9 0 0 0 9 0 0 0 9. So this is equal to 6 minus 5 5 minus 5 6 minus 5 5 minus 5 6 minus. Okay, let me add these two. I can always do that because this is plus, this is plus. So 6 plus 9, it is 15. 6 plus 9, it is 15. 6 plus 9, it is 15. minus now 6 to 12, 616, 616 minus 6 and 6. Then 6 to 12, 616 minus 6 and 12. So what is your A inverse? 1 by 4 times 15 minus 12. It is 3 minus 5. 3. Then 15 minus 12 minus 5 minus plus 6. It is 1. 5 minus 6 is minus 1. So it will be 1 and minus 1 over here because this is symmetric matrix. 15 minus 12 is 3. Minus 5 plus 6 is 1. It's 1 over here and this is 3. This is your A inverse. This is A inverse of this matrix. Very simple. You don't have to find adjoint, then determinant, cofactors, minors, etc. Okay. So this is how we can find the inverse of a matrix using Caley-Hamilton theorem. I will be forwarding questions to you. You have to do it of your own. I will show you one more method how to find the inverse of a matrix, which depends on elementary transformations. Inverse by elementary transformations. See, what I will do is that I will write, for example, let me find inverse of A. This is a square matrix of order n. I will write A into I into A. There is no harm. What I will do is that I will use elementary operations to this A on the left hand side of 1 and the prefactor I, this I of 1 till I get, I will not do anything to this A. So I'll get this as I, this as some other matrix B, and this is A. This is A as it is, this is B, this I has been turned into B and A into I. Now this is the definition of the inverse. Square matrix B is said to be inverse of A if AB is equal to BA is equal to I. So B is called the, this will be the inverse. Okay. You can always write A as A into I. And you can operate this and this till this becomes B. This becomes I. And this is as it is, this becomes B. And this is definition. By definition, this will be an inverse. But for this prefactor, I have to use only row transformations. This is theorem. And for post factor, I have to use column transformations only. This you have to remember. Okay. Let me take up a question. Very simple question and then I will take your leave. See, A equal, we have just now seen, it is 1, 2, 3, 4. I can write A as I into A, means A 1, 2, 3, 4 as 1, 0, 0, 1 and this A as it is. Let me use operations. I have to make this A I. This some other matrix. So operate row 2 minus thrice row 1. What I will get? 1, 2, 0, 4 minus 6, which is minus 2. Same transformation have to be used for this matrix. 1, 0, row 2 minus thrice and this A. Now with the help of this, I can make this 0. So operate row 1 plus row 2. I have 1, 2 minus 2 plus 0, 0 minus 2 equal to this plus this, it is minus 2. This plus this is 1 minus 3 and 1. And this is A. Now finally, I have to make this 1. So operate minus 1 by 2 times row 2. I have to use only row transformations. I will get, what I will get? 0, 1, 0, sorry. 1, 0, 0, 1. What I have done? Minus 2, 1, and this is your A, 1, 2, 3, 4. Now I have used minus